Okay, hi folks, it's the turn of the 2019 National 5 Physics paper, multiple choice section. And there are 25 questions in this paper. This was the first year it went to 25 questions in the multiple choice. And as usual, first thing you see then is the data sheet. That contains all the numbers that you might need to help you do the questions in the paper. Let's get going then. Question 1. Which of the following are both vectors? Well, remember, all the quantities that we use in physics are either scalars or vectors. Scalars only have size, but vectors have size and the direction. Now, you only need to know about 5 vectors, so let's make a little list of them. There are loads of scalars, but there's only 5 vectors that you need to remember. And if you remember the 5 vectors, then everything else goes on the side of the scalars. And those 5 vectors are displacement, velocity, acceleration, force, and weight. Everything else is a scalar. Time, energy, mass, distance, speed, temperature, you name it, everything else. So let's have a look at the question. Which of the following are both vectors? Let's look at A. Weight and acceleration. Yes, they're both vectors. Let's check the other ones though. Energy. Nope. Energy is a scalar. What about in C? Mass. Nope. Mass is a scalar. D. Speed. Speed's a scalar. And E. Oh, there's speed again. Speed is a scalar. So there's only one vector in all the other answers, so both vectors is answer A. Moving on then, question 2. A car is travelling at 6 metres per second along a straight road. The car then accelerates at 2 metres per second squared for 4 seconds. What's the final speed of the car? Well, we need our acceleration equation. Might be useful to put it in a triangle because it's V we're looking for. So V minus U equals A times T. So V minus the starting speed. We're told that the car was travelling at 6 metres per second. That's its initial speed. And that's going to equal to the acceleration, which was 2 times the time, which was 4. So V minus 6 equals 8. So V must be 14 metres per second. And that's answer B. Question 3. The graph shows how the speed of a car varies with time. During which part of the journey does the car have the greatest acceleration? Well, acceleration is the slope of the velocity time graph. So the steeper the slope, the greater the acceleration. So whereabouts on our graph is the slope of the graph the steepest? That's the bit with the greatest acceleration. Well, that appears to be the little section between S and T. So the gradient is the steepest. So greatest acceleration there between S and T. That corresponds then to answer 3E. Moving on, question 4. This is a projectiles question. A ball is kicked horizontally off a high river bank as shown at 8 metres per second. And the ball lands on the lower river bank 2 seconds later. The river bank's 3 metres wide. We have to calculate the distance between the edge of the lower river bank and point X. Well, first thing we need to do then is work out how far the ball goes. It's distance equals speed times time, 8 metres per second, and it's in the air for 2 seconds, so it's going to go 16 metres. But we know that the river is 3 metres wide. So what's the distance going to be on the other side of the river? Well, that whole distance there is 16 metres. So the distance that we are looking for is going to be 16 minus 3 is 13 metres. And that corresponds to answer 4C. Quite tricky. Question 5. Okay, we've got a table here that tells us the distance from the Earth at the surface temperature and the age of 5 stars. So distance, temperature and age. And it's a triple statement question. A student makes the following statements and we have to say if they are true or false. As the distance from the Earth increases, the age of the star decreases. Well, there's the distance increasing. Let's have a look at the age. So 2.4 times 10 to the 8, that's the oldest one. And then as we go down, well, the next oldest one is that one. The next oldest one, oh, this is tricky because 1 times 10 to the 7 is the same as 10 times 10 to the 6. So that's the next oldest one. That's the third oldest one. And then 8 times 10 to the 6 is the fourth oldest one. And 7.9 times 10 to the 6 is the youngest one. So there's not really any order to that at all. So as the distance goes up, the age decreases? No, it doesn't. It's all kind of mixed up. Statement 2. As the age of the star increases, the approximate surface temperature increases. Does that mean the oldest one is the hottest then? Well, the oldest one is the first row. Well, it's not the hottest one. Is the youngest one? No, the youngest one isn't the coolest either. So no, statement 2 is wrong as well. And statement 3, there's no apparent relationship between the distance and the temperature. Yes, that one's true. Distance has got nothing to do with the temperature. That's really tough. 3 only. That's 5C. That was horrible. Right, moving on. Question 6. A geostationary satellite orbits the Earth. Which row in the table shows the altitude above the surface of the Earth and the period of the geostationary satellite? Well, if it's geostationary, then it's going to take 1 day to go around the Earth, same as the Earth takes to go around. And 1 day is 24 hours. So it's either going to be B or E, and a geostationary orbit is at 36,000 kilometres above the Earth's surface. So 6B. Question 7. The weight of a robot on the Earth is 240 newtons. What would the weight of the robot on Mars be? Well, Mars is smaller than the Earth, so it's going to be smaller than 240, but we should really work out its mass first. If we can work out its mass from M equals W over G, that's 240 over 9.8, because 240 is its weight on Earth. And the mass of that robot is 24.5 kilograms. Now, mass doesn't change. If that's its mass on Earth, then that is going to be its mass on Mars as well. And if we want to calculate its weight on Mars, then it's going to be mass times gravity on Mars. So the mass was 24.5, but the gravity on Mars, we're going to have to go and scroll all the way back up to our data sheet and look up the table of gravitational field strengths and look for Mars. So gravitational field strength is on the left there, and Mars is 3.7. So let's pop that into the question. The weight on Mars will be M times G, 24.5 times 3.7 gives us an answer of 91 newtons. That's answer C. That's another pretty tricky one. A lot of work to do there just for 1 mark. Okay, moving on. Question 8. We're on to electricity now. A hairdryer is connected to a 230 volt supply I make a list whenever I see numbers in the question. I'll make a little list. So the voltage is 230 volts. The current in the hairdryer was 2 amps. The electrical charge that passes through the hairdryer, we don't know, but the time is 5 minutes. Well, 5 minutes is 300 seconds. Always good to turn your time into seconds. It's Q we're looking for, so Q equals I times T. That's 2 times 300 is 600 coulombs. 600 coulombs is answer C. And you'll notice the voltage had nothing to do with this. That 230 volts there just was to put us off. Question 9. The graph shows how the resistance of a thermistor varies with temperature. So as the temperature goes up, the resistance is going down. And the thermistor is connected in a circuit. And at a temperature of 50 degrees, the current is 0.004 amps. Well, if we read the graph as well, at 50 degrees, the resistance is 2 kilo ohms. That's 2,000 ohms. So if we know what the resistance is, it's 2,000 ohms. And we know what the current is, it's 0.004 amps. We can work out the voltage as the current times the resistance, which is 8 volts. That's answer D. Question 10. Student sets up the circuit shown below. In which circuit will both LEDs be lit? Remember, an LED has to be connected the correct way around. And if we look at the LED symbol, it's got a kind of triangle in its symbol. And that triangle in the symbol should always point to the negative terminal. The tip of the triangle must point to the negative terminal of the battery. So in answer A, the first one's the correct way around, the tip's pointing at the negative terminal, but the other one is the wrong way around, and they're in parallel, so only one of them would be lit up. In answer B, that one's the wrong way around, and they're in series, so none of them will light up. Same in part C, that's the wrong way around, none will light up. Same with D, that one's the wrong way around. And in E, the tip of the triangle, yes, and yes, they are both pointing the right way. So E, they will both light up. But in B, C, and D, if one of them is the right way around, but the other one is the wrong way around, then none of them will light up. If one of them's the wrong way around in a series circuit, it will stop the current flowing. So even though an LED is the right way, it's pointing the right way, well, that one's pointing the wrong way. That one is pointing the right way, and that one's pointing the right way, but they won't be lit up because of the other LED in the circuit. That's really tricky as well. Very difficult paper, this. So E, both of them pointing the right way. Let's move on. Question 11. Electronic circuit has got an LDR in it. We're told the room temperature is 20 degrees, the lamp is off, and the lamp will light when, well, let's think about this. It's an LDR, and you should know about an LDR is that when it gets dark, the resistance of the LDR goes up. So the voltage across the LDR will increase when it gets dark, and then the transistor will switch on. So the lamp will light when the light level is decreased below a certain value. That's answer A. So answer A is correct. B is wrong because that says the light level would have to increase. And C is wrong because we don't want to increase the resistor. We don't want to reduce the battery voltage. So it can only be answer A that is correct. The light level is decreased below a certain value. When it gets dark, the transistor switches on. Question 12. It's a mixed series and parallel circuit, and a student makes the following statements about the readings on the meters. And we have to figure out which of these statements must always be true. Well, we don't know what the resistor values are. These resistors could be anything we want. So for these statements to always be true, bearing in mind the resistors might be different, then will V1 always equal V2? Well, no, it might not. Not if the resistors are different, it won't. Statement 2, V2 equals V3. Yes, always. If two resistors in parallel, they each get the same voltage across them, always. And statement 3, Vs, the supply voltage is equal to V1 plus V2. Yes, that's always true as well. Series voltages will always add up to the supply voltage. So V1 plus V2 equals Vs, always. So that's statement 2 and 3 only. That's answer D. Another tricky one. Question 13. Solid substance is placed in an insulated container and heated. The graph shows the temperature varying with time. So it starts off solid at point P. So at Q, where the temperature stays the same, it must be melting. And then it's heated up again, and at S, it must be evaporating. And we are asked to calculate the specific latent heat of fusion. Then we would use the time from section. Well, fusion's when it's melting. So the time section that we are going to use when the substance is melting is going to be section Q to R. And section Q to R is answer B. Question 14. Now, there's usually always a question somewhere in your paper with an unknown equation. It's an equation you've never seen before. But don't panic, because they will tell you what all the symbols mean, and they'll tell you all the numbers apart from the one you've got to work out. So in this case, we've to work out the depth of the liquid. We're told what the density is, and it's 990. We're told what the pressure is, it's 1470. We know that G is 9.8, and we've to work out the depth. We're told the depth is the symbol H. So let's put this equation in a triangle and then rearrange it to work out what H is. So H will be equal to P over that kind of curly P symbol times G. So the pressure was 1470 divided by, and I would put this in brackets, the density, 990 times G, which is 9.8. And if you do that on your calculator, you're going to get an answer of 0.15 meters. That's answer B, 14B. 15. A car is parked in the sun for some time, and during this time the pressure in the tyres will increase. And the reason for this increase in pressure is the volume occupied by the air particles in the tyres has increased. Well, no, the tyres stay the same size, so that's wrong. The force produced by the air particles in the tyres acts over a smaller area. No, tyres are the same size. Average spacing between the particles is increased. No, because the tyres are the same size. The increased temperature makes the air particles expand. Nope, particles don't change size. The air particles move with greater kinetic energy. Yes, they do. The hotter they are, the faster they move, the greater the pressure. 15E. 16. The temperature of a gas is 20 degrees. As soon as you see a temperature that's in degrees Celsius in a gas laws question, change it into Kelvin. Remember, to change it into Kelvin, you add 273 to your Celsius temperature. So 20 plus 273 is 293. 293 Kelvin. And the volume is 0.3 cubic meters. And the container is free to expand in order to maintain a constant pressure. And the temperature of the gas is increased to 50 degrees C. Well, again, I would change that into Kelvin right away. So the second temperature will be 273 plus 50 is 323 Kelvin. Now, I would make a list of all of these things then, and then pick the right gas law that we're going to use. So we know that V1 is equal to the first volume was equal to 0.3 cubic meters. The first temperature was 293 Kelvin. The second volume is what we've defined, and the second temperature was 323 Kelvin. So the gas law that we want to use is V1 over T1 equals V2 over T2. That's Charles' law. And then we want to rearrange that to find V2. It might be easier putting the numbers in first. So V1 0.3 over 293 equals V2 over 323. So if we multiply both sides by 323, we'll get V2. So 0.3 times 323 over 293 gives us an answer of 0.33 cubic meters. The volume only goes up by a very small amount because the temperature's only going up by a small amount. So temperature goes up, volume goes up. That's answer D. Okay, moving on then. Question 17. This is waves. The following diagram gives information about a wave. Which row in the table shows the amplitude and the wavelength of the waves? Well, I'm going to draw a line right through the middle. Remember, amplitude is the height measured from the middle to a peak. So it'll be half of the 6 meters, which is 3 meters. That's the amplitude. So it means we can only be answer A or B. What about the wavelength of the wave? Well, we've got 1, 2, we've got 3 complete wavelengths there in a distance of 24 meters. So 3 waves in 24 meters means that one wavelength must only be 24 divided by 3 is 8 meters. So if a wavelength is 8 meters and we know the amplitude was 3 meters, then our answer must be B, 17B. 18. Students studying waves with a period of 80 milliseconds and a wavelength of 4 meters. What's the frequency of these waves? Well, we've got an equation on our equation sheet. Frequency equals 1 over the period. So if we do 1 divided by 80 milliseconds, 80 milliseconds is 80 times 10 to the minus 3. If you do that on your calculator, you get an answer of 12.5 hertz. That's 18C. Question 19 then, still on waves. Which of the following diagrams shows the diffraction of water waves as they pass between two walls? Well, diffraction is the bending of waves around an obstacle, and when waves diffract, their wavelength doesn't change. But what we do know is that long waves will diffract more. They will be bent around an obstacle more than short waves will. So let's look at each of these diagrams in turn and see what's happening. So in diagram A, there's no diffraction taking place at all. Those waves aren't being bent, they're just kind of chopped off. In part B, the waves are kind of curved in the middle section, so that's not right either. They should still be straight waves in the middle, so that's not right. In answer C, well, the wavelength of the waves has changed, and wavelength doesn't change. They don't get closer together, so that's wrong. D looks okay. We'll come back to that though. What about part E? Well, part E again, the wavelength's changed. The waves are more spread out. That doesn't happen. Wavelength stays the same, so that's wrong. So, looking at all of them, the only one that's correct or looks correct is answer D. So, wavelength stays the same, but the waves are bent around the obstacle. Question 20. This is a ray of light passing through a glass block. And first thing to notice from this diagram is that the angles should always be measured relative to the normal. These angles aren't, so we need to fill in. The angle to the normal is 60 in air and 35 in the glass. Now, what are we asked? Which row in the table shows the angle of incidence and the corresponding angle of refraction? Well, watch the direction of the arrow showing the ray of light's direction here. The arrow is showing us that it's travelling through the glass first and then into the air. So the angle of incidence will be the angle in the glass, and the angle of refraction will be the angle when it comes back out into the air again. It's going through glass into air. So the angle of incidence will be the 35 and the angle of refraction will be the 60. So 35 and 60 is answer A. Very tricky. 21. Which row in the table shows the path taken by an alpha particle and gamma radiation as they pass through an electric field between two metal plates? Well, there's an alpha particle that's positively charged and a gamma ray has no charge, it's just an electromagnetic wave. So alpha particles will be attracted to a negative plate. So which of our diagrams shows us that? Well, answer A is wrong because it's got it being attracted up to the positive plate. Answer B would be okay. Answer B is okay for our alpha particle. Answer C, no, that's wrong way it's been attracted. Same way answer D is wrong and answer E is okay. But what about our gamma ray? Well, gamma rays are uncharged, so they should go straight through. They won't be bent at all. So B is okay for our gamma ray, and if that's okay and that's okay, then it's answer B. 22. Nuclear radiation for a particular source, 1,800 atoms decay in 3 minutes. What's the activity of the source? Well, there's the relationship A equals N over T, where N is the number of decays and T is the time in seconds. 3 minutes is 180 seconds, so that's 10 becquerels. Answer A. 22 A. 23. The crew on an aircraft during a transatlantic flight are exposed to cosmic radiation at a rate of 5 microsieverts per hour. That's what they get every hour, 5 microsieverts. Now the average duration of a flight is 8 hours and they do 6 flights every month. So 6 8s is 48 hours. So every month they fly for 48 hours and they get an equivalent dose rate of 5 microsieverts every hour. So 5 times 48 is 240 microsieverts, but that'll be per month. And because there are 12 months in a year, then per year it's going to be 240 times 12. 2880 microsieverts. 23E. 24. A radioactive tracer is injected into a patient to enable doctors to check the function of their kidneys. And radiation is monitored outside the patient's body with a detector. Well, if it's outside the body, we're going to have to use gamma radiation. And also, if you're injecting this tracer into a patient, you don't want it being there for too long. So 6 hours is answer D. 24D. We've got there the last one. The activity of a radioactive source is 56 megabecquerels. If the activity 40 hours later is only 3.5 megabecquerels, what's the half-life of the source? We draw our little table. 2 rows in the table. The first row will be activity, and it will be in megabecquerels in this case. The time on the bottom will be in hours. At the start, the time is 0 and the activity was 56. What do we do with that 56? We keep halving it. Just keep halving. Just keep halving. Half of 56 will be 28. And then you keep halving it until you get down to the number that you're looking for, which in this case is 3.5. So half of 28 is 14. Half of 14 is 7, and half of 7 is 3.5. Now that's what we're looking for, and that took 40 hours. So let's fill in the gaps. It'll be 10, 20, 30, 40. So how long did it take to fall to half its original value from 56 down to 28? That took a time of 10 hours. So the half-life of the source is 10 hours. And that corresponds then to answer B, 25B. Well, that's the 2019 multiple choice paper, paper 125 questions. I was trying to do it in less than half an hour. It's taken me just slightly over half an hour. You would only have 45 minutes to do it. It's pretty tough. Make sure you look over that a couple of times, and we'll see you in the next one.